Beep. I will begin with a word of prayer. I think it's time, right? So, dear Father, we thank you for this day. I thank you for the weekend just completed. Just help us to glorify what we do this day, Lord. In your name I pray, Lord Jesus. Amen. All right, let's see. So, this is the day before the test, even though, of course, the test isn't until Friday. But Wednesday doesn't exist as far as we're concerned, right? Are you guys gonna like sleep all day Wednesday? Like, what's your plans? Do you have some annoying professor who's like scheduled a lecture for it? I think my daughter does. Let's see here. You guys probably don't care about L'Hopital's rule, right? Should I put a question on L'Hopital's rule in the test? Sure.
If you tell us it's going to be. Are you going to tell us every question this time?
Probably not.
Darn.
Let's see here. But we can talk about what reasonable questions on the test look like. As judged by me, not as judged by you, of course. Let's see here. I will eventually find the solution I just scanned. Where'd you go? Wait a minute, where'd I save it? Oh, man. Oh, there it is. All right. Sorry for the delay. I should probably top hat. I don't seem to find my attendance sheet today. All right. Yeah, I'll top hat. Give me a second. Do. Look, you guys are number one on the list. There we go.
Never gets old.
All right. Here is problem 76. I think this is pretty straightforward. Basically, the key is the product rule, it doesn't commute, right? So you have to maintain the order of products. And then you have a triple product, you do the triple product rule. Again, you end up with it like this. A prime, AA prime A, AA prime, if you like. Let's see here. Imagine writing the product rule for n things. You'd need a new notation for it, wouldn't you? Let's see here. So, what? Well, I think we just, wasn't there another? Oh, okay, never mind. I got it. So here's 77. So let's see here. So I calculate the characteristic equation. We find eigenvalues -1 and 3. And then I found eigenvectors. Now, so at the moment, like, you'll see at least 3 different ways I find eigenvectors in this solution. This is kind of my middle of the road. I look at it and I go, duh. So there's just one equation apparently, which is 2u plus 2v equal to 0, which means v is minus u, so bam, right? There is a error in the last lecture that was brought to my attention afterwards, because certain ones of you take perverse joy in making corrections after class. But you all saw it. There's a place where I put a minus where I should have put a plus, or vice versa. And if you didn't notice it, well, oh well. It's not good. That means you're just copying stuff and not thinking, which I guess is a middle ground. But you should think at some point, preferably before the test, or during the test. Think during the test, that's good. But anyway, so the second one obviously is just the equation u equals v done twice. So you might wonder, where's the u equals 1 come from? In both cases, I just choose it, right? Because we're just looking for a representative eigenvector, right? And then this, where does this come from? Well, this comes from the derivation I did the Friday before spring break, right? We decoupled, we integrated, and we found that there were two constants like that. Or if you like, it comes from chapter 9 in Nagel, Snaff, and Snyder, if you're in the 334 course. But that is the general solution. The general solution, outside of having an initial condition, should have two constants in it for a second order problem, for a 2 by 2 problem. You should have three constants in it for a 3 by 3, et cetera, like n constants for an n by n problem. So there's that. This one here caused me much suffering in terms of, like, I don't know, every time I correct a sign mistake, a sign error in my determinant, something else would go haywire. Yeah?
If we write the general solution as vector r, do we have to write x and y solutions?
It depends on the instructions. If I just said write the general solution, it's ambiguous. You can go either way. So I'm just writing both for the convenience of the grader, but I don't intend for them to take off points if you don't write the scalar solutions. That is the expectation of some people, but I don't. I personally like the vector form of the solution. It's kind of more orderly, especially if you've got initial conditions. On the other hand, the matrix technique is a technique to solve the differential equations in x and y. So like finding the formulas for x and y separately is an interesting thing. So I can see both sides of it. Anyway, so factoring lambda minus 2 out of that cubic is not entirely trivial. Like the lambda squared is free, the 126 is free, but the 45 in the middle, the long division helps, right? Another way that you could do it, things to look for, right? You know that the trace is the sum of the eigenvalues, right? So if the trace is 18 plus 29, that's 39 plus, what, 8? 47. So you know that as you're factoring this, that has to come in play, right? Like if the sum of the eigenvalues is 47, then the product of those numbers has to be 252. That could be helpful in the factoring, in principle. Maybe not for this one. For this one, I threw you a bone, right? I'm like lambda equal to 2 as a 0. So that's like super helpful, because that means you can factor out lambda minus 2. But maybe that sum of the eigenvalues being 47 is helpful when you get to here, right? Because this shows you there's an eigenvalue of 2, which means that there's eigenvalues 45 left over. That means that whatever this factors to, the sum of the eigenvalues has to be 45. Of course, you knew that from basic factoring anyway. So I'm not telling you, maybe I'm not telling you anything terribly interesting, but there's how it factors. Now, if you didn't have all this algebra in your solution, I don't think necessarily we'd take off points here. Because I did say you could use technology, so I don't know. I think it's hard for us to take off points going forward. But on the other hand, you do need to think about, is this a reasonable problem for a test, right? And the answer is yes. Not 3 of them, but 1 of them, yeah. Now, I don't have the work, but I think it's probably pretty easy to find the eigenvectors here. Minus 1, 1, 0, 1, 1, 1, and minus 1, minus 1, 2. You can go back up to the matrix and easily check that that matrix times that vector, the matrix times that vector is twice the vector. The matrix times that vector is thrice the vector. The matrix times the U3 is 42 times U3, right? So that's how I check. That's how I tend to check eigenvectors. I like take the matrix that's allegedly the eigenvector 4, multiply the matrix by the vector, see if I actually do get the multiple of the vector I'm supposed to. Because if I don't, I did something wrong, you know? So just as a double check on the solutions. And then, so here it is. There's the solution, C1, C2, C3. You got your 2, your 3, and your 42. So here's the other way I tend to sometimes calculate. And this is totally, wholly unnecessary here, right? Like this is like a stupid way. I just was trying to fill the paper with stuff, you know? So a minus 4, we're given the eigenvalue is 4. So I'm trying to find eigenvector with eigenvalue 4. I do 4 minus the 10 minus 4 minus 2 minus 4 gives me the 6 and the minus 6, and then the 4 and the minus 9 right along. And then I just do row reduction until I get to row ref, at which point I can read off that u minus 3/2 v is equal to 0, so u is 3/2 v, and then I just pick, v equals to 2 to keep fractions out of our business. Apparently, Dr. Sperano thinks I planned to have wind damage in my house, like it was some kind of conspiracy. It's just a fortunate happenstance that I wasn't there Friday, and that he ended up getting the pie in his face, up his nose. It's unfortunate, isn't it? If somebody asks me if I'll do one of those in the future year, I'll probably have to be like, no, I can't. My house might get broken again. I don't know. I don't want future wind damage to my house. If you guys don't know what I'm talking about, I was scheduled to go to this Professor Pieface thing last Friday, but then my house had stuff blow off of it, which I had to fix before the rain. So, which we fixed. It was good, but anyway. Let's see here. So, this one, let's see, what did I do? A minus I, and I just row reduce, right? And at this point, I'm like, I don't feel the need to reduce all the way to the row ref, right? By the time you get to 3, 2 with a row of zeros, there's a quick trick. What you do is just flip the numbers and put a minus on one of them. That'll be an eigenvector, if you're looking at that, right? So that's all I did is I take the 3 and the 2, flip them around, put a minus on one of them. That will make when I multiply that vector times this matrix, it'll give you 0. I don't even think about it. I just flip, put a minus. There's a quick trick for you. Of course, you can think through the equation too. It's not like a big deal, v plus 2v equals to 0. So, u plus 2v equal to 0. So u is equal to minus 2v. So if I put v equals to minus 1, I get u equals to 2. But what I did here wasn't that. I just thought about this. I looked at it. I flipped it. I put a minus on one of them. You say, well, why'd you put the minus on the v on the second component and not on the first? I don't know. There's no reason. All right, it's very ad hoc. This is the trouble I face. If I give you a problem like this on the test, I say, here's a 2 by 2 matrix. Find a basis for each eigenspace, right? That's just a fancy way for me saying, find an eigenvector with each eigenvalue, a token representative of each one. There's not a unique answer, right? Like, there's infinitely many answers, so I have to grade these real careful, right? But it's easy enough for me to do, because all I have to do is take your answer and multiply it by the original matrix and see if I get back, the vector again for lambda equaled 1, or 5 times the vector for my u2. It's easy to check. And also, once you find 1, you know that any other eigenvector is going to be a multiple of your original one. Unless you've got 2 dimensions in the eigenspace, and then it's more tricky, but we'll get to that. Okay, so like this one, a little bit more, I can't just do my flip and put the minus sign trick because it's a little more complicated. But here I actually did honest to goodness row reduction. I put the row I like the most into the top row, and then I use it to get rid of the pivot down to first column. And then what did I do? I just added 3 times the second row to the third row to get the zeros here, at which point I'm like, okay, that's good. Because I see that I have rank 2, which is what I'd like. Actually, I don't know. A priori, like before the fact, without further calculation, somebody tells me eigenvalue minus 2 for this matrix. I don't know whether that 2 is repeated or not. See, if the eigenvalue 2 is repeated in the characteristic equation, there could be 2 eigenvectors, right? It could be that all 3 equations are the same equation, which would leave me 2 free parameters, which would leave me needing 2 vectors for my eigenbasis for eigenvalue 2, minus 2. Now, that didn't happen here, because actually the a plus 2i equations are actually just two independent equations, which leave me 1 free parameter, w. And anyway, long story short, I put w equal to 3, and there's my eigenvector. So, again, if you didn't show this work, I don't feel like we can take points off you because I said you could use technology for the homework going forward, right? So if you just shove this into the, you know, the calculator and said, well, that's the eigenvector, I don't see as we can really take points off you. On the other hand, if you did that for every single one of them, you're in a bad place for the test, you know? So, I don't know. Let's see here. This one, I don't see as there is any kind of especially, nothing yells at, oh, no. I don't see any like super slick way of making this like ridiculously easy. I was really hoping what would happen. So it's pretty obvious that with lambda equals to 4, you get these zeros here, which immediately tells you that like E4 is an eigenvector with eigenvalue 4. All right. E4 times the matrix is the 4th column in the matrix, right? Rather, the matrix times E4 is the 4th column, which is 4E4. So yes, E4 is an eigenvector with eigenvalue 4. I can see that without like writing stuff down. But what I had hoped is that this matrix here, what's left over, right? If that was invertible, which I could quickly check by calculating the determinant, right? If that determinant had been non-zero, then I already know what would happen. I know that this would row reduce to the identity matrix with a 0. That didn't happen though, right? This determinant 0, which speaks to the reality that this 3 by 3 matrix is in fact not full rank. It's not rank 3, it's not invertible. It will not row reduce to the identity matrix, so I have no choice but to calculate. So I calculated. If this had turned out different, I was just going to write equals identity matrix with 0 and be done. That would have been it. But it didn't turn out that way, right? But I left this here just so you know one of my tricks, okay? And the trick is just that if you've got like a submatrix, you can judge whether or not it's going to, you know, like row reduce to the identity by checking whether or not it's invertible, because we have this theorem that a block of diagonal matrix is invertible if and only if like the blocks are separately invertible. Remember that? Like A, B, block inverse is A inverse, block inverse. So you can kind of generalize that even when one of the blocks is 0. Obviously we can't invert the 0, but okay, I shut up. So at this point, it becomes quite obvious that this row and that row are the same row, so just keep one of them, you know, and then we're done. So that's enough. Now I can see that, I started using subscripts because U, V, W, what comes next? X? I don't know, I decided to use U1, U2, U3, U4 for this one. So U1 is minus, aw man, seriously? Not cool. Well, there's a mistake. So, you guys would have told me about that today though, right? Okay. You know who you are. And so that was supposed to be U1 is equal to 2U3 because I forgot about this minus here. And that makes U2 3U3 and U4 and U3 are free. I think this one I didn't check, which was dumb. So that gave me, you know, and you should recognize this. This is the null space basis calculation, right? That's what we're doing again and again, the null space basis calculation. So this is supposed to be a 2, not a minus 2, right? Once I correct it. But otherwise, we're good, right? And yeah. Any questions? I can just go on, but so this says, without calculation, find one eigenvalue and 2 linearly independent eigenvectors. So you look at that and you go, well, clearly the column vectors are linearly dependent, right? Or if you like, the determinant's obviously 0. Whatever first pops to your mind, it's clear that this is not an invertible matrix, right? And we learned that if it's not invertible, then lambda equals to 0 is an eigenvalue. So that's what I can see without further calculation. Lambda equal to 0 is an eigenvalue. And once I know that, I'm just looking for vectors that when you multiply by the matrix, they give you back 0. And it's pretty easy to see that 1, -1, 0, and 0, 1, -1 are good choices there, right? And those are linearly independent. Why? Because they're clearly not scalar multiples of each other, right? So for two vectors, to judge linear independence, it suffices to notice that they're not linear dependent. They're not scalar multiples of one another. Now, even though it told me not to, I decided to do some calculations. And by the way, guys, it's up to you. You don't have to. You have two choices, right? You can either do determinant of a minus lambda I and work it out that way, right? Or sometimes I like to do determinant of xi minus a and work it out like that, because I'm just less likely to make a mistake in algebra if I use x as opposed to lambda. It's dumb, but it's true. I have to admit it. So, and I don't like the way my t looks. Some people would use t for the polynomial here, which is probably what we'll do in 321. You'll just have to suffer with my poorly written t. But anyway, I decided this one to try some of the row operation calculation, see if it helps. And I think it did a little bit. So did you guys see what I did? Going from like the top one to the second one, what did I do? What's the difference? What did I do? Going from the top line to the middle one. Subtracted row 3 from row 1. No, I think you're right. Subtracted row 3 from row, you had it right. So that makes the 5s cancel, right? And just leaves you x0 minus x. Yeah. And then I decided to do what? And then I think I took a row
3 minus row 2.
Yeah, row 3 minus row 2, that's what I did. And so the 5s again canceled, and it left me with an x and a minus x and an x. And then I thought, well, that's kind of an improvement. Now I've only got one x minus 5. And then I did the usual. I think what I did was can you guys tell me what expansion, how did I calculate the determinant? What did I use? I think what I did was I expanded on the first column. See, this is x times this guy, the determinant of x times x minus 5 and minus 5x. And then, oh, maybe I did the top cross row though.
I think you did that.
Huh. Oh yeah, I guess it was the top. I used the top row. Never mind. I'm thinking somewhere else in my solution I expanded on the first column. I've just forgotten where I did which. Anyway, it worked out. And so you notice what happened here is we got lambda equal to 0 and lambda equal to 15. So there's another answer to this problem. Some of you might have just looked at it and go, 15 has to be an eigenvalue, right? Because 0 is obviously an eigenvalue. The trace is obviously 15. That doesn't really force it to be 15, right? It could be 0, 5, and 10, or it could have been 0, 4, and 11. I mean, there's a lot of other possibilities, but once you know that 0 is an eigenvalue, and you know that there's 2 eigenvectors, that forces there to just be one eigenvalue left, because if you have 2 linearly independent eigenvectors, that means that your algebraic multiplicity of 0 had to be 2. Which means you can have at most one more eigenvalue in your characteristic equation. And so it's not surprising that we just have one other eigenvalue, namely 15. This, of course, is not part of the solution. I'm just playing around with this example because it's kind of a nice example. It's also the reason I didn't get the solution to the last 2 problems written. Sorry. I should have done that instead, but oh well. 25. We pretty much worked this in class. Let me not belabor that one. 83, when I looked at this problem, I didn't read it carefully enough, because if I had, I wouldn't have signed it. This problem's like, there's nothing to it. I mean, you're like, well, that's not a bad thing, right? Did it feel like nothing to you, though? Maybe it didn't feel like nothing to you. Felt like something? Was it a thing? So, like xk plus 1, literally you just put in k plus 1 to the formula, and yay. And then a times xk, well, I just multiplied a by that. I pulled out the constants like c1 and lambda to the k and c2 and mu to the k, and that gave me au and av, but by assumption that's lambda u and that's mu v, which gives me this and that, which is that. So, yay, I guess. I feel like there's a more interesting problem that could be created from the ashes of this problem or something. I don't know. Like a phoenix. Let's see here. I think these, you're just supposed to calculate the characteristic equation, right? So I did that, and I chose to do the xi minus a form. Again, you don't have to do it that way. You can do it with the lambdas if you wanted instead. And I don't think you had to factor it, right? Like I factored it because I think it's interesting, but you didn't have to factor this, right? This one's actually kind of interesting because when you, oh, this is the one I did. First column, I expanded on the first column. I think this one's actually kind of interesting because you end up being able to factor an x minus 1 out. See, there's a common one here and here. So this actually is a really, really nice matrix as far as they go for finding a 3x3 characteristic equation. It's just quite nice. And it's got integer eigenvalues, but anyway, there it is. Any questions? I mean, we can double check our work, right? This should be the product of the eigenvalues, plus or minus, depending on how I set things up, right? See, it's minus a. See that? Minus a. So it's a 3x3. What happens when you plug in x equal to 0? You got the determinant of minus a. What is the determinant of minus a when it's a 3x3? Do you guys know about this? I hope you know about this. This is part of what's on the test, right? We haven't tested determinants yet, right? So one of the critical things about the determinant is if the determinant is c times a, it's c to the n times the determinant of a, right? So if we're talking about the determinant of minus a, we've got minus 1 in this example here to the 3 determinant of a, right? And so that's why that 28 in the characteristic polynomial is not the determinant, it's minus the determinant, which is good because the eigenvalues here are 1, 7, and minus 4, the product of which is the determinant, the product of which is minus 28. Right, so that all gels. And also the sum of the eigenvalues, 1 plus 7 minus 4 is 4, which is also equal to the trace of that matrix. Right? As I've been trying to sell you guys on, these are useful checks on our calculations. Determinant's product of the eigenvalues, trace is the sum. The other important identity which it would be most unfortunate for you to go to the test without a clear understanding of is that triangular matrices have easy eigenvalues, right? If the matrix is triangular, you can read the eigenvalues straight off the diagonal. So I look at that, I got 5 minus 4, 1, 1. Those are my eigenvalues. This one, I've got 3, 1, 0, 1, 3. So I've got 3 eigenvalues, 2 1 eigenvalues, and a 0 eigenvalue. That immediately allows me to write down the characteristic equations by the factor theorem. Some of you, doubtless, did this a much harder way, right? Well, not much harder. You just write determinant a minus lambda I and it's diagonal, right? So you just, bloop, there's the characteristic equation. It's the same thing, right? But I don't even have to do that. See, because I can work backwards from the factor theorem. If I know zeros of the characteristic polynomial, then I can write down the characteristic polynomial using the factor theorem. You guys know what I'm talking about with factor theorem, right?
Yes.
Okay. As in f of c equals to 0 if and only if x minus c is a factor. You're like, we just said we knew. Fine. All right. This one's just kind of ugly. So it's easy enough to check that v1 is an eigenvector with eigenvalue 1, v2 is an eigenvector with eigenvalue 0.5, v3 is an eigenvector with eigenvalue 0.2, right? So, if I give a question like this on the test, recognize it for what it is. What would that problem be?
3 points.
Free points, that's right, it's a gift. So if a gift is given, please freely receive it, And there has to be some of that sort of thing on this test, right? Like, part of the test has to be, here's some data, how do you work with it? That is part of what we're doing. So there are ways of shortening things by just giving you, hey, here's a matrix, here's the eigenvalues, here's the eigenvectors. Do certain things that we've learned how to do. You can do that. But anyway, when I calculated, so you guys might have a better argument than I do. I don't know. I mean, basically the argument for me why there exists C1, C2, C3 is just that you've got v1, v2, and v3. They're eigenvectors. They have distinct eigenvalues. One of the theorems that I told you guys is that if you have distinct eigenvalues, you've got linearly independent eigenvectors. So if I've got 3 eigenvectors with 3 distinct eigenvalues, it's necessarily the case that they're linearly independent. But if I have 3 linearly independent vectors in R3, that's a basis. All right. And as such, there exists C1, C2, and C3 such that X naught's in the span of those guys. I don't know if there may be a more explicit argument you could have given here, but that's the one that I would like to give, so I gave it. And so then W transpose times X naught is nothing more than the dot product of W and X naught, which gives us alpha plus beta plus gamma, which was my notation for the components of X naught. You might have labeled them something else. I just made up the alpha, beta, gamma, right? That's just my solution. You call them whatever you want. But the sum of whatever you want to call them is 1. And on the other hand, W is perpendicular to V2 and V3, and its dot product with V1 is equal to 1. So that leaves you with 1 equals to C1, which is what you're supposed to show in part B. In part C, well, we kind of did this calculation in class, right? When you hit a power of a matrix times an eigenvector, we get the eigenvalue to that power times the vector, right? We worked this out for like V squared and V cubed. So I'm just applying that result again here. And well, what happens is that the 2 and the 3 eigenvalues are less than 1. So if you got a fraction less than 1 and you raise it to an infinite power, it goes to 0. Whereas if you have 1 and you raise it to the infinite power, well, it's just 1. So yeah, xk goes to C1 V1, which is just V1, which is what we're asked to show. So this actually kind of walks you through the theoretical backdrop for what happens with the stochastic matrix problem. I claim that there exists a steady state vector to such a problem, and this kind of walks you through the theory for how that looks like in the specific instance of a particular 3x3 example. Problem 86 I like a lot. This is a really cool application of diagonalization, right? What does diagonalization do for us? It allows us to calculate all kinds of different stuff that we couldn't otherwise do. I mean, I guess you could try to calculate a to the power k and just like calculate a squared, calculate a cubed, calculate a to the 4th, and start looking for patterns, right? Find a pattern and then prove that it's true by induction if you wanted, I guess. But man, this is so much easier. If we have a diagonalization, we can calculate the kth power of a by just calculating the kth power of the diagonal form of a and then doing this similarity transformation here. I really like these matrices too, by the way. Aren't these nice? Like this has what? Determinant what? 3 minus 4, which is minus 1, right? And this one also has determinant minus 1. So like they're very nice matrices to invert. Those are the kind of matrices you're supposed to find me lots and lots of for your computer project, which I'll remind you about right now. I want more of those. Create me more of those. No, I mean the computer project's not on the test. I have. Will those be on the test? I mean, they could be. Let's see here. Was this? I'm trying to remember what they told us. I think this one I just have. Oh, I was just supposed to diagonalize A. That was the instructions. So I plugged the matrix into the website. I found that the eigenvalues were 1 and 3 repeated, and those are the eigenvectors. So I take those, I put them in a matrix, I do P inverse AP, and what pops out is that. That's how you diagonalize. So that's it. Now, this would be a prime example. Yes?
Does it matter what order the diagonals are in? Like if you, like...
Oh, no. You could, yeah, you could in principle. If I flipped like the first and the third columns here, that would flip this 3 and the 1. It would put a 3 up here and a 1 down here. Yeah, there's not a unique diagonalization. It's unique up to reordering. So yeah, there's other answers for true. So this would be a good example of the kind where it would be wise for me to give you a problem like this, where I give you data, and then I say diagonalize it. So all you have to do is take the things you're given and just form a matrix. And I might, if I was, well, I don't know. if I actually wanted you to work out the inverse of the matrix, I might say, work out the inverse of the matrix explicitly, if I actually wanted you to do that, right? Or I might say, work out the inverse of the basis matrix explicitly, or if possible, use a theorem so you don't actually have to work it out. What theorem would we use so we don't actually have to work it out? Orthogonal, right? So, like, if, for instance, if I had, I don't know, 1/3 minus 2/3, let's say 2/3, and I had, I don't know, 1/√2. Oh man, what have I done? Rats. Ooh. Well, 0, 1/√2, 1/√2. That is perpendicular to that. They both have length 1, right? If I want to complete this to a orthonormal basis for R3, what's my third vector have to be? Do you know how to do that? Fill in the blank here. What would I put? If this is, let's say, V and this is W as vectors, I'll put vector signs on them to make you less nervous about this. What goes in the blank if I want this to be a orthonormal basis? There are two choices. One is the right-handed choice, one is the left-handed choice. So one is correct, one is evil. Yeah?
They're cross product?
They're cross product, right? Yeah, you could do that. So if we was to do V cross W, then that would be a orthonormal basis. And so if I was to take the basis matrix beta, which would be U, oh my bad, what's wrong with me? Many things, but nothing. V, W, V cross W. That matrix has the wonderful property that the inverse is equal to the transpose. By homework problem 48, was it? I forget which one. We had a homework problem where we worked this out. Maybe that would be a good test question to work that out. But let's see here. So yeah, the complex eigenvalues here work out to 4 plus or minus I, and so then I chose the plus one to actually find the eigenvector 4. So A minus 4 minus I. The 5 minus 4 is minus 1, and then I get the minus I. 3 minus 4 is minus 1, then I get the minus I. And over here, I'm just double checking. I'm just double checking that my two equations are actually scalar multiples of one another, just as a redundancy check on my calculation. So in particular, what I'm doing is I'm doing 1 minus I times, I'm doing this one here, minus 1 minus I times 1 minus I, and I work that out, I get minus 2. That's good. That shows me that the first equation is simply 1. The first equation is simply 1 minus I times the second equation. Is what I'm checking. So good. This is not necessary. Like, this isn't really part of the required part of the solution by any means, but it's comforting to me. So anyway, pick whichever one of these you like. I'll pick the second one. U is equal to 1 plus I times V. Hopefully I didn't make a sign mistake this time. I put V equal to 1. That gives me U equals to 1 plus I, which gives me this eigenvector for eigenvalue 4 plus I. The book instructions told us to find a complex eigenbasis for each complex eigenspace. So there's one of them. The other one is just take the complex conjugate. 1 minus I, 1 is the basis for the complex lambda equals 4 minus I eigenspace. So you get that. And then I tacked on the question, solve the real equation, right? Solve the differential equation. And so there I used our theorem that we worked out in class. Namely that you do a constant times e to the real part of the eigenvalue, cosine of beta t, which here beta is 1, And I used the 4 plus I one. So I got the 1, 1 here and the 1, 0 here. That's the real and the imaginary part of the complex eigenvector. And then over here, again, the A and the B, quote unquote, sine plus cosine as opposed to the cosine minus sine. Did I let you guys have a page of notes or something? Yeah, I probably would want to have the real solution for the complex eigenvector problem on your formula sheet, right? You know, just that probably something you want to do. That's where my solution ends for today. Sorry, I don't have the other ones written out yet. I'll hopefully have them a little bit later. Let's see here. Let's take a walk down memory lane. Let's look at mission 4 for a second. Simpler times, right? But this is on your test, right? So like your test has what are the things on the test? It's everything we've covered since chapter 1, right? I mean, since test 1. Listen to me. I'm a dummy. So we got determinants. You get all your handy-dandy determinant trick formulas. The things we learned about block matrices for determinants are helpful. We have this theorem on invertibility of a matrix, right? So we can either talk about the determinant is non-zero, or the it's come back to me.
It was just in there.
Oh, well, did we hand it around yet? Well, let's get nuts. Oh, Kramer's rule. Hey, we learned Kramer's rule. I forgot about Kramer's rule. Yeah, it guts to have your Kramer rule. There's Kramer's rule. We have studied much about. This has been talked about a lot in here at this point. That if we have similar matrices, right, that B is P inverse AP, then they share the same determinant, they share the same trace, right? So being able to apply those to a problem or being able to prove it. That's the kind of proof I do think you should be able to do in here. Like explain why, if B is equal to P inverse AP, why is it that the determinant of B is equal to the determinant of A? Why is it that the trace of B is equal to the trace of A? In other words, I think you should take ownership of this calculation right here and this calculation right here. There's not much there, really. I am not suggesting that on the next test you have to prove that the trace of AB is equal to the trace of BA, and also that the determinant of a product is the product of the determinants. I would never ask you to prove that in here, because that's technical. Row swapping switches your determinant by -1, right? We had the volume theorem, right? If you've got 3 vectors in 3 dimensions, you want to calculate the volume of the parallelepiped with the vectors as edges, you just slap the vectors in the determinant, you calculate the determinant, there's your volume up to a sign. We had that. What else did we? We had, we had these properties for, so this is a really good one to review in terms of just helping you remember properties of the determinant, which we sometimes use. Some of these we haven't used that much, right? Like I don't think we've used the determinant of the power of the matrix is the determinant of the matrix to the power. Like I don't remember using that identity, but now that I'm looking at it and thinking about making your test, well, that's the downside of reviewing, I suppose. Here's the equation of the line. Yeah, so that's kind of cool. And then we had mission 5, was it? I can't count. What was in that? Ooh. Oh, we did learn what a linear transformation was, didn't we? So we also could be tested on what? Like the matrix of a linear transformation. How to find the matrix with respect to a non-standard basis. We did that, right? I would strongly suggest that you have a clear statement of how to find coordinates for a vector. Right? This formula that the beta coordinate vector is beta inverse times x, like that's important. You should know how to work with that. Because certainly there should be questions on the test about the coordinate vector thing. And finding the matrix of a transformation with respect to a different basis, like this T beta beta business here. That is, of course, interesting. Let's see here. Anything else to tell you about? Problem 62, I think, was interesting. I hope you look at that and compare how I did it to how you did it, right? Actually, I did it two ways, right? I did it abstractly, just using, the formula for coordinate change. And then I also suffered through what I think I intended for you to do, which was to look at the explicit change of basis formulas between the x and the y coordinates and add those together. And yeah, so yeah. Sometimes to find coordinates, it's really just, it takes us back to test 1, right? Like this is a reality. There's probably some problem on the test where you actually do need to do row reduction, but there's probably a lot where you don't. So don't assume that every problem requires calculation. Don't be surprised that some do, would be my general point of order for the test. Problem 64 is a great test question because it requires almost no calculation. It's completely conceptual. Basically, the point of problem 64 is, do you understand what a basis is and how it works? So the basis is an ordered set. You have to write A, B, C, D as a sum of E2, E3, E4, and E1 in that order. And so that forces me to rearrange the letters basically in this pattern, and then the coefficients, B, C, D, and A, are the coordinate vectors with respect to the basis. So make sure you understand problem 64. This is a very easy test question if you understand it, and it's a very unpleasant test question if all you have on your formula sheet is that the coordinate vector is beta inverse times x, and you feel the need to actually calculate beta inverse here, because there's no need for that, right? Like explicit, just mindless calculation here would be very much the wrong way to do this problem, I mean, it wouldn't take you too long, I don't think, to calculate the inverse of the basis matrix here, but it's way easier than that. Yeah? Almost done. What else? Finding the standard matrix. I would put this in the category of a free gift. Yes? What's not a free gift is, here's a linear transformation. Is it one-to-one? Is it onto? Right? We talked about that as well, so you need to review. How do we figure out if the matrix is one-to-one? That means that the null space of the standard matrix is 0. Right? If the null space of the standard matrix is not 0, that means that the transformation is not one-to-one. How is it onto? It's onto if the rank of the matrix is the same dimension as the place where the transformation is mapping into. So we have those two things, one-to-one and onto, only possible if we're going from the same dimension, which means that the determinant of the matrix had to be non-zero. And anyway, I would just, as usual, review if you would, please review the solutions, and hopefully everything will go peachy Friday. So, thanks, guys. And just